Welcome to this lesson on basic data analysis. Today we're going to learn how to perform simple but meaningful data analysis using scientific methods. So what exactly is data analysis? Data analysis is the process of examining, cleaning, transforming, and interpreting data to discover useful information and support decision-making. Think of it like being a detective, but instead of looking for clues at a crime scene, you're looking for patterns and meaning in numbers. The most important principle in data analysis is this: you must let the data speak for it. Your interpretation must follow the numbers, not your personal expectations or biases. Let's work with a real example. Imagine we conducted an experiment measuring plant height in centimeters after giving them different amounts of fertilizer. Here's our data. We have 5 measurements. 0 grams of fertilizer gave us 5.2 centimeters of height. 1 gram gave 7.1 centimeters. And so on up to 4 grams giving 13.5 centimeters. The first step in any data analysis is to visualize your data by plotting it on a graph. This helps you see patterns that might not be obvious in a table. Here's our scatter plot. Each red dot represents one data point. The x-axis shows fertilizer amount, the y-axis shows plant height. Notice how the points seem to follow an upward trend. Now let me ask you a question. What pattern do you see in this data? The answer is, we see a positive correlation. As fertilizer increases, plant height increases. But we need to be more quantitative than just saying it looks like it goes up. Step 2 is calculating basic statistics, starting with the mean, which is the average value. The mean is calculated by adding up all your values and dividing by the number of values. We write it as x bar equals the sum of x sub I divided by n. For our plant heights, we add 5.2 plus 7.1 plus 8.9 plus 11.2 plus 13.5, then divide by 5. This gives us 45.9 divided by 5, which equals 9.18 centimeters. This is the average height of our plants. The mean tells you the central tendency, or the typical value around which your data clusters. It's like the center of gravity of your dataset. Next, we calculate standard deviation, which measures how spread out your data is from the mean. Standard deviation S equals the square root of the sum of x sub I minus x bar squared, divided by n minus 1. Think of standard deviation as roughly the average distance that data points are away from the mean. It quantifies the scatter, or variability. Let's calculate it step by step for our data. First data point, 5.2 minus 9.18 squared equals 15.84. Second point, 7.1 minus 9.18 squared equals 4.33. If we continue this for all 5 points and add them up, we get 34.16. Then we divide by n minus 1, which is 4, giving 8.54. The square root of 8.54 is 2.92 centimeters. So our standard deviation is 2.92 centimeters. This tells us that on average, our plant heights deviate from the mean by about 3 centimeters. You might ask, why do we divide by n minus 1 instead of n? The answer is that dividing by n minus 1 gives us an unbiased estimate of the population standard deviation when we're working with a sample. This is called Bessel's correction. Step 4 is adding error bars to our plot. Error bars visually represent the uncertainty or variability in our measurements. Here's our plot with error bars shown in yellow. Each vertical bar extends above and below the data point, typically by 1 standard deviation or standard error. Error bars show the range of uncertainty in each measurement. Larger error bars mean more uncertainty, smaller ones mean more precision. Step 5 is identifying trends. A trend is a general direction or pattern in the data over time or across conditions. For our plant data, we have what looks like a linear trend. The data roughly follows a straight line. We can draw a best fit line through the data shown in green. This line represents the overall trend and helps us make predictions. The equation of this line is our trend equation. For a linear relationship, it has the form y equals mx plus b. Y equals mx plus b, where m is the slope and b is the y-intercept. For our data, The slope is approximately 2.0 centimeters per gram of fertilizer. This means each additional gram of fertilizer adds about 2 centimeters of height. Now let's discuss something critical: distinguishing between real patterns and random scatter. Here's an analogy. Think of your data like listening to a radio. The real pattern is the signal, the music you want to hear. Random scatter is the noise, the static that interferes. The signal is the real pattern, systematic and repeatable. The noise is random scatter, unsystematic and unpredictable. So how do we distinguish between signal and noise? How do we know if a pattern is real or just random chance? Method 1 is to calculate the correlation coefficient R. This quantifies the strength of a linear relationship. R equals the sum of x sub I minus x bar times y sub I minus y bar divided by the square root of the sum of x sub I minus x bar squared times the sum of y sub I minus y bar squared. The correlation coefficient R always ranges from -1 to +1. R equals 1 means perfect positive correlation. When x increases, y increases proportionally with no scatter. R equals 0 means no linear correlation. The variables are independent, there's only random scatter. R equals -1 means perfect negative correlation. When x increases, y decreases proportionally. For our plant data, if we calculate R, we get approximately 0.998. This is very close to 1, indicating a very strong positive correlation. Method 2 is visual inspection. Look at how much scatter there is around the trend line. On the left, we have tight scatter where points cluster closely around a trend line. This suggests a real pattern. On the right, we have wide scatter where points are all over the place. This suggests mostly noise. Method 3 is statistical significance testing, like a p-value test. This tells you the probability that your observed pattern could have occurred by random chance. Typically, if p is less than 0.05, we say the result is statistically significant. This means there's less than a 5% chance the pattern is due to random noise. Now I need to give you a critical warning about confirmation bias. Confirmation bias is the tendency to see what you expect to see in the data, rather than what's actually there. For example, you expect fertilizer to help plants grow. So when you look at your data, you might unconsciously ignore data points that don't fit this expectation. The solution is to always follow the numbers. Calculate the statistics objectively. Let the data tell you the story. Don't force your story onto the data. Here's an analogy. A good scientist is like a judge, not a lawyer. A lawyer tries to make the evidence support their case. A judge looks at all the evidence impartially and reaches a conclusion based solely on what the evidence shows. Let's look at a real-world example with temperature data over time. Here's temperature data from 2015 to 2020. The temperatures range from 14.8 to 15.3 degrees Celsius. Question: is there a warming trend in this data? Answer: we need to calculate the statistics first before jumping to conclusions. The mean temperature is 15.05 degrees Celsius. The standard deviation is 0.19 degrees Celsius. This is quite small, indicating low variability. The total range is only 0.5 degrees over 6 years. That's less than 0.1 degrees per year on average. With such small changes relative to natural variability, we would need much more data over a longer time period to confidently identify a real warming trend versus random fluctuation. Let me give you some practical tips for doing good data analysis. Tip 1. Always plot your data first. A graph reveals patterns that a table of numbers might hide. Tip 2. Calculate multiple statistics. Don't rely on just the mean. Also calculate standard deviation, median, range, and correlation. Tip 3. Consider outliers carefully. An outlier is a data point that's far from the others. It might be a measurement error, or it might be revealing something important. Tip 4. Always check your units and scales. A common mistake is mixing up units like centimeters and meters, or using the wrong scale on your graph axis. Tip 5. Replicate and verify. One dataset is never enough. Good science requires repeating measurements and having others verify your results. Now let's talk about common mistakes people make in data analysis. Mistake 1 is cherry-picking data. This means only showing the data points that support your conclusion while hiding the ones that don't. Mistake 2 is ignoring uncertainty. Every measurement has some uncertainty. Reporting a single number without error bars is misleading. Mistake 3 is confusing correlation with causation. Just because two variables are correlated doesn't mean one causes the other. For example, ice cream sales correlate with drowning deaths. But ice cream doesn't cause drowning. Both are caused by a third factor: hot weather. Mistake 4 is using inappropriate statistics. For example, using mean for highly skewed data where median would be more appropriate. Mistake 5 is overinterpreting small samples. With only 3 or 4 data points, you can draw strong conclusions about trends. Let me introduce one more advanced concept: standard error. Standard error equals S divided by the square root of n, where S is the standard deviation and n is the sample size. While standard deviation measures the spread of your data, standard error measures the uncertainty in your calculated mean. Notice that as n increases, standard error decreases. Larger samples give you more confidence in your mean value. For our plant data, standard error equals 2.92 divided by the square root of 5, which is 1.31 centimeters. We would report this as: the mean height is 9.18 plus or minus 1.31 centimeters. Let me emphasize again the importance of honest interpretation. Science is fundamentally about discovering truth, not about proving what you already believe. If your data contradicts your hypothesis, you must accept that. Don't manipulate the analysis to get the result you want. Remember that negative results are still valuable results. Finding that two variables are not correlated is just as important as finding that they are. Let's work through one complete example problem analyzing reaction time data. We measured reaction times in milliseconds for 8 people performing a simple button press task. Here's the data. Reaction times range from 238 to 255 milliseconds. Step 1. Calculate the mean. Add all 8 values and divide by 8. 245 plus 238 plus 252 plus 241 plus 248 plus 255 plus 243 plus 250, all divided by 8. This equals 1972 divided by 8, which gives us 246.5 milliseconds. Step 2. Calculate standard deviation using our formula. We calculate each deviation from the mean, square it, sum them all, divide by n minus 1, and take the square root. This gives us a standard deviation of 5.73 milliseconds. Step 3. Calculate standard error. Standard error equals 5.73 divided by the square root of 8, which is 2.03 milliseconds. Step 4. Report the result with proper uncertainty. The mean reaction time is 246.5 plus or minus 2.0 milliseconds. This means we're confident the true population mean is somewhere between 244 and 249 milliseconds. Let me give you a final summary of the 4 pillars of good data analysis. Pillar 1 is visualization. Always plot your data to see patterns visually. Pillar 2 is quantification. Calculate key statistics like mean, standard deviation, and correlation. Pillar 3 is uncertainty. Always report error bars and indicate your level of confidence. Pillar 4 is objectivity. Follow where the data leads, not where your expectations want it to go. Remember this key principle. Numbers don't lie, but people can misinterpret them. Your job as a scientist is to interpret honestly and accurately. The more you practice these techniques, the better you'll become at spotting real patterns, avoiding bias, and drawing valid conclusions from data.